After establishing the role of gas flow rate on the bubble size distribution, we wanted to further identify some bubble size distribution determining factor. And for that, we took two different nozzle diameter. One is for 2 mm nozzle diameter, and the second one is for from the current research, which is 0.4 mm nozzle diameter. And we found that when we use a smaller nozzle diameter that time, the number of bubbles were increased and the average diameter of the bubbles was reduced. Same things can be observed from this graph at different gas flow rates. So from here, we can say that bubble size increases with increasing nozzle diameter and decreasing injection velocity. Let's move on to the next slide and talk about what is happening with the bubbles formed in the continuous casting mold. So in here you can see I have put different shadow graphs from lowest percentage FG to the highest percentage FG, and you can see here from the lowest percentage FG we have very small bubbles, and for the highest percentage FG we have big bubbles. And number of bubbles we can also find the number of bubbles from this graph. You can see when we are increasing the percentage FG, number of bubbles are increasing initially, then after a certain percentage FG value, it starts to reduce. So what is happening here? Number of bubbles are reducing, but the size of the bubbles are increasing. It means that gas is contributed to increase the size of the bubbles rather than their number. But to confirm, so this is the impact of gas on the size of the bubble size distribution of the bubbles formed in the mold model. To know it further, we change the liquid velocity, liquid flow rate, as well as in the new set of experiments. So you can see here, these are the results when we took two different liquid flow rate. One is for 3.5 LPM and another one is for 4.5 LPM. So at lower liquid flow rate, the Sauter mean diameter was high, and at higher flow rate, the Sauter mean diameter or the mean bubble diameter was less. The same thing can be observed here, that at lower liquid flow rate, the number of bubbles were less, but at higher liquid flow rate, the number of bubbles were high. It means that there is an impact of liquid flow rate. So what is happening basically here? Liquid flow rate is having a shearing effect on the bubbles, and that causes the reduction in the size of the bubbles, as well as increment in the number of the bubbles. So in case of mold model, the responsible factor for VSD is both gas flow rate as well as liquid flow rate. Let's